Bismillah ar-Rahman ar-Rahim. Today we're going to talk about chapter 23, lecture 3, electric potential due to continuous charge distribution. So in this lecture we will discuss and we will try to calculate the electric potential due to continuous charge distribution, and we will study the electric potential due to the conductor. Let's start by the first slide. If the charge distribution is known, we can calculate the electric potential due to small element of charge dq. And in this case, dV equal k dq over r. If we want to calculate the total electric potential due to all these element of charge dq, in this case, we will try to calculate the integration. That means the electric potential at any point P due to all these small charge element of charge dq is equal k, the primitive of dq over r. And this is the equation of the electric potential due to continuous charge distribution. It's similar to the electric field E due to for the continuous charge distribution. In lecture 3 of chapter 22, we said that the electric field is equal k integration of dq over r squared. We will follow the same steps that we did before. We will try to calculate or to express dq, the distance r, and the sides of the integration, and then the integral. If the charge distribution is highly symmetric, when it's highly symmetric, we can use Gauss's law to get the electric field. Starting from the electric field, we can get the electric potential difference. How? You remember that the equation of the electric potential difference is equal delta V equal VB minus VA equal minus the path integral from A to B of E ds. This is used when we have a highly symmetric distribution of charge. Okay, so to get the potential difference in this case, we have to come back to chapter 22, lecture 2, Gauss's law. Gauss's law. Okay, starting from the electric field, we can get the electric potential. If we want to calculate the electric potential at a specific point, what we're going to do in this case, we will take the electric potential at the point A is 0. So that means the point A will be located at infinity. Why? Because V infinity equal 0. And in this case, we can determine the electric potential at the point P, not the difference between A and B. No, it's the electric potential at the point B. When we take A at infinity, so we can get the electric potential at the point B. Okay, we are done. Just we will take some examples and we will move to the electric potential due to conductor. Question A said, a ring of radius A carries a uniformly distributed positive charge Q. Find an expression of the electric potential V at a point P lying at the distance x from the center along the central axis perpendicular to the plan of the ring. You see here that we have a ring. The radius of the ring is A, and you have a point P. This point P is at a distance x from the center of the ring, but it's also located on the central axis perpendicular to the plan of the ring. Why this is very important? Because we will get an idea about the distance r from the charge dq to the point P. As usual, let's try to solve step by step. Okay. He's asking about the electric potential at the point P. You see here that we have a ring. ring. That means discrete or continuous charge distribution. In this case, V equal K integration of dq over R. As I said in the previous slide, we must express R, we must express dq, and then the expression of the sides of the integral, and then we calculate our integral. Let's start by the first one, R. As you see, R is equal square root of x squared plus a squared, because we have a right angle triangle. Then dq, before discussing dq, it's linear distribution, sorry, we talk. Before discussing dq, what we're gonna say? If we put dq here, if we change the location of dq, what happened to the distance r? If we put dq here, what happened to the distance r? If we put dq here, what happened to the distance r? If we put dq here, what happened to the distance r? You see that in all the cases, r is the same. R. Okay? R is the same, whatever the location of dq. Why? Because, as we said here, P, the point P, is located at the central axis perpendicular to the plane of the ring. So that means any point from this ring to the point P is equal to R. So we can conclude that R is independent of the location of the Q. It's independent on the location of the Q. So to be considered as constant. Okay? That's all. We will keep the Q because we will talk about the integral of the Q and dq, because there is no relationship between R, the distance, and dq. And then we can say that the electric potential is equal K over R, that means over square root of x squared plus a squared, the path integral of dq. The integration of dq only gives the total charge Q. So we can say that the electric potential at the point P is equal K Q over square root of x squared plus a squared. And we are done. This is the expression of the electric field produced by a ring at a point P lying on the central axis perpendicular to the ring. It's okay? So here we consider that R is a constant. This is very important. It's not the case for the other examples. We are done. Okay? Question B, for sure, he will ask about the electric field. What he said here, find an expression of the electric field E at the point P. That means, of course, starting from the electric potential expression. We have the expression of the electric potential. Question B. Good. He's asking about the electric field from this equation. As you know, we have a relationship between the electric field and the electric potential. We said in the previous lecture, E equal minus gradient of V. Okay, so that means starting from the electric potential, we can get the electric field. However, you see that V depends only on X. We have just one variable. All the other terms are constant. Only the variable is X. So this expression becomes the x component of the electric field is minus dV over dx. Okay, so what we're gonna do to get the electric field along x? Just we will differentiate this equation to get minus kq is constant, d over dv, d over dx of 1 over square root of x squared plus a squared. So it will be x squared plus a squared power minus 1 over 2. Don't forget that we have a mathematical equation said f power n prime equal n f prime fn minus 1. This is our our function f, and this is our n. Okay, so let's move. Ex will be minus kq, as usual, the constants, multiplied by n, that means multiplied by minus 1 over 2, multiplied by f prime, that means 2x, multiplied by fn minus 1, that means x squared plus a squared, power minus 1 over 2 minus 1, so it will be minus 3 over 2. And that's all. This is the electric field. We have 1 over 2 and 2. We have negative sign and negative sign. And then we're going to get the electric field at the point P equal KQX divided by x squared plus a squared power 3 over 2. And this is our electric field at the point P. We are done. Let's move to the next question. And the next question, he said, find the electric potential and the electric field at the center of the ring. At the center. Question C said, at the center. At the center of the ring means x equals 0. For the electric potential, V, when x equals 0, is equal KQ over square root of a squared is a. KQ over a. That's all. What about the electric field when x equals 0? It's KQ. Here we have 0. So it's 0 divided by a squared. So it's 0. We are done. At the center of the ring, the electric field is 0, but the electric potential is KQ over R. Good. We are done. Let's take another example. A disk of radius A has uniform surface charge density. So here we are talking about surface charge density. When we talk about surface charge density, the charge Q is equal sigma multiplied by the surface area. Okay, question A said, find the electric potential V at a point P lying at the x-axis from the center along the central axis perpendicular to the plane of the disk. Okay, so as usual, let's try to get this figure and let's try to solve step by step. Here also we have continuous charge distribution, so the electric potential V will be equal K integral of dq over R. As we said before, we have to express our dq, our distance R, and our integral. To avoid any confusion between the two, the variable R and this R, we will write, we will take a dq over here, a small element of charge dq. The distance from the center of the disk to the point dq is y, or let's say it's d. It's y. It's better. Y. Okay. And the distance from dq to the point P we will say that it's a D. Okay? Let's say here it's R. Okay, to keep the same. The distance from the center to the point DQ is R, but the distance from DQ to the point P is D. So here we have to switch the R to D, because we are talking in the expression the distance from the charge to the point P. Okay, so what we're gonna do? At first, in our case, dq is what? dq is sigma dA. Good. Sigma dA. And what do you think about D? Is, as you said here, square root R squared plus X squared. Good. So what we're going to do in this case? What we will do? dq is not constant. If we take another location of dq over here, we have a distance d1. Let's say this is dq1. d1 different from d. So we can conclude that the distance r depends on the location of dq. So it's not constant like the previous example, it's a variable. It's not constant because it depends on the location, on r, the location of dq. It depends on r. Okay, r is the distance from dq to the pointer or the origin of this disk. Okay. And you see here that dA for the disk, 2 pi r dr. And you can say that dq equal sigma dA 2 pi r dr. So we are done. We write the expression of the electric potential equal K, integration of dq. dq is what? Let's write here, all the constants are outside. 2 pi sigma r dr, all of them are constant. Sigma, the integration of r dr over square root of r squared plus x squared. This r, the distance from the center to the point dq, varies from where to where? It's varying from 0 to the maximum. That means from 0 to A. Good. It's varying from 0 to A. Now we have to calculate this integral. This integral will be given, and okay, as we said, the integral from 0 to A of 2r dr over square root of r squared plus x squared is equal to 2 square root of x squared plus a squared. So then we can write our electric potential V equal K pi sigma multiplied by 2 square root of x squared, of r squared plus x squared, r squared plus x squared from 0 to A. This 2, it can be outside, so we can write 2 pi sigma K, factor of square root of A squared plus x squared minus square root of, now the r is 0, so square root of x squared. Square root of x squared is only the absolute value of x. And if x is positive, so we write it only x. So here we have x is positive. Very good. And we are done. This is the expression of the electric potential at the point P. Let's move to the next question. And the next question, he said, find the expression of the magnitude of the electric field at the point P. is asking the electric field. As we did in the previous example, you see that the electric potential depends only on X. So what we're gonna do, we will write the X component of the electric field is equal minus dVx over dx. So just we want to differentiate this equation to get the electric field. To do that, we write Ax equal minus, all the constants will be out of the integration, out of the derivation, minus 2 pi sigma k d over dx of what? Of x squared plus a squared power 1 over 2 minus x. We are done. It will be equal minus 2 pi sigma k d over the x of this function. Don't forget that we have f power n prime. It will be n f prime fn minus 1. So here our n is the half. So we write half of what? F prime. So 2x multiplied by fn minus 1. So it will be x squared plus a squared 1 over 2 minus 1. So it will be minus 1 over 2. Now let's talk about the derivative of x. The derivative of x over x, it will be minus 1. That's all. We are done. You see here that we have half and 2. We will cancel this. So we're going to get minus 2 pi sigma k x, let's a factor of x over square root of x squared plus a squared minus 1. That's all. So we can write the x component, the magnitude of the x component to be 2 pi sigma k factor of 1 minus x over square root of x squared plus a squared. That's all. This is the electric field at the point P, starting from the electric potential and using the equation, the electric field is equal minus gradient of V. We are done. Let's see if we have any other question. No, we are done. We don't have any other question. Okay, so let's take another example. In this example, the question said a rod of a length L located along the x-axis and has a total charge Q, and a charge per unit of length lambda equal Q over L. Find the electric potential at the point P that is located on the y-axis, a distance a from the origin. Okay. We take the figure and let's start to do it. As usual, we have continuous charge distribution. So the electric potential B is equal K, the integral of dq over R. As you know, we have to calculate dq, we have to calculate R, and we have to integrate. In our case, dq is what? Is lambda dl, but dl in our case is equal dx. Why? Because the charge dq is varying along the x-axis. So we write dx because it's along x-axis. Okay, let's move to the R. R is the distance from dq to the point P. We have a right angle triangle, so it will be square root of x squared plus a squared. Did R depends on dq? Yes. If we take another dq here, let's say dq1, we have a distance r1, different from R. So we can say that R depends on dq location. Good. Very good. So then we can write V equal K lambda, it's constant, the integration of the x over square root of x squared plus a squared. Good. The sides of the integral are the following. dq is varying from 0 to the maximum, to the other edge of the other side of the rod. So it's varying from 0 to L. Very good. Now we are done. We have to calculate this integral. Okay, this integral will be given. So the integral of the x over x squared plus a squared power 1 over 2 is equal ln x plus square root of x squared plus a squared. So we can write v equal k lambda, the constant, multiplied by ln x plus square root of x squared plus a squared from 0 to L. So v will be equal k lambda ln, at first we substitute by L, ln L plus square root L squared plus a squared. Good. Minus ln, now we substitute x by 0. ln 0 plus square root of 0 plus a squared. So it will be ln a. You know that ln a minus ln b is equal ln a over b. So we can use this rule to say that the electric potential V equal K lambda multiplied by ln L plus square root of L squared plus A squared over A. And we are done. This is our electric potential at the point P due to this configuration. Okay, good. Let's move. We are done. Now let's take another example. In this example, the electric charge Q is distributed uniformly along a line or a thin rod of a length to A, sorry. Here we have A, and here we have A. Find the electric potential P along the perpendicular bisector of the rod at a distance x from its center. So now P is located on the perpendicular bisector. That means it's passing, this axis is passing by the center of this rod. Okay, so what we're gonna do in this case it will be easier. Of course, we have continuous charge distribution. So we will write V equal, question A, V equal K, the integral of dq over R. As usual, dq is equal lambda dl, and our charge is varying along the y-axis, so lambda dy, and R equal square root of x squared plus y squared, because here we have right angle triangle. Okay, and you see that dq is written as a function dy, and R depends on y, so is variable, not constant, because it depends on dq location. So what we're gonna do, we will write V equal K, the path integral of dq is lambda dy, so we write lambda outside because it's constant, dy over square root of x squared plus y squared. So the charge dq is varying from where to where? It's varying from minus A to A along the rod, minus A to A. Very good. We're gonna use this expression to calculate the integral, the same like before. Now we have to calculate this integral. Okay, so the electric potential at the point P equal K lambda multiplied by ln y plus square root of x squared plus y squared is varying from minus a to a. So it will be k lambda factor of ln. Now we will substitute by a plus square root of x squared plus a squared. Our variable is y, not x, minus ln minus a plus square root of x squared plus minus a squared, so it will be plus a squared. The negative sign would be cancelled. As usual, we have ln a minus ln b, so it will be ln a minus b. So we can write v equal k lambda ln a plus square root of x squared plus a squared over minus a plus square root of x squared plus a power 2. And we are done. This is the expression of the electric potential at the point P. Yes. Good. We take another example. In this example, we have an insulating sphere of radius r, has a uniform volume density and total charge Q. Now we are talking about insulating sphere, because later on we will talk about the conducting sphere. The question, find the electric potential at the point outside the sphere. And we take the potential is zero at infinity. Good. Here, what do we have? Let's come back to our objective. In the objective, we said we will calculate the electric potential due to continuous charge distribution we are time. And we will study the electric field, electric potential due to conductor. But here, we said that we have two cases. The first case, if the charge distribution is known, dq. And the second case, if we have highly symmetric charge distribution. Okay? Highly symmetric charge distribution, what we said that we're going to refer to Gauss's law. The sphere is highly symmetric. The volume charge distribution of the sphere is highly symmetric. Highly symmetric distribution. Highly symmetric distribution, so we're going to use Gauss's law to get the electric field, and then we will get the electric potential. So from chapter 22, lecture 2, the electric field outside, how much is outside? Is kq over r squared. And r is the distance from the center to the point, let's say it's a point P. Okay? So in this case, what we're going to do, we know that the electric potential difference equal minus integration of E ds. Our electric field is radial. E is radial. Okay? It depends on R. So in this case, so EDS as dot product will be equivalent to E, depends on R, dr cosine theta. And since the electric field is radial, so cosine theta is 1. We will cancel this cosine theta. So the electric potential in this case becomes what? The difference of the electric potential is minus the integral of E dr. So we can write it's kq constant minus kq constant, the path integral of dr over r squared. Okay? But here, the sides from where to where? The question said we want to calculate at a point outside. What we said when we calculate at a point, at specific point, we choose a point A at infinity. Point A at infinity to get VA equals 0. So we will choose our first point at infinity. So the first point is at infinity, and the second point at the point P here. So we will calculate the potential difference between infinity and the point P. Why? Because V of infinity equals 0. It's okay? So we write delta V equal V at the point P minus V at infinity. V of infinity is the electric potential at infinity is 0. So here we will calculate only the electric potential at the point P. So that means V at the point P equal minus KQ, the integral of dr over R from infinity to the point P, that means to the coordinate R squared. The primitive of 1 over R squared is minus 1 over R. So we can write minus KQ minus 1 over R from infinity to the point P, that means to the coordinate R. We have negative sign and negative sign. They will cancel each other, and we're going to get V at the point P outside of the sphere equal KQ factor of R minus 1 over infinity. And this is 0. The electric field, the electric potential at infinity is 0. And we can conclude that the electric potential at the point P outside is equal KQ over R. Very good. We are done. Okay. Second question. They said find the electric field, the electric potential at the point inside the sphere. What do we have? Starting from the equation delta V equal minus, minus EDS, we know that E at the surface, how much the electric field at the surface? It's KQ over the radius squared. Our radius is capital R over R squared. Okay? Chapter 22, lecture 2. Very good. So if we want to calculate an electric field inside, for example, at the point D, we're going to get the difference between the electric field at the center, electric potential at the center and the point D. So what we're going to do here, we will write delta V between a point on the surface and the point inside equal VD inside minus VC on the surface, which is equal minus KQ over R minus KQ the integral of E inside dr, because we said that the electric field is radial. We know that E inside the insulating charged sphere equal KQ R over radius cube. Okay? Don't forget that this VC is at the surface. And VD is inside. Our objective is to calculate VD. So we can say that VD equal VC minus KQ, the integral of, sorry, here without KQ. KQ, the integral of R dr, and here we have over R cube. Good, we are done. So what is the integral of r is r squared over 2? From where to where here? From the point C to the point D. Point C is at the surface, that means at the distance r. Point D is inside, that means at the distance small r variable. And r is smaller than capital R. So we can write that the electric potential at the point D equal the electric potential at the surface KQ over capital R. This is VC at the surface minus KQ over R cube of what? Of R squared over 2. And we will write 2 here. From where to where? From R, capital R to small r. So what we're going to get? We will get KQ over R minus KQ over 2R cube multiplied by R squared and plus KQ over 2R cube multiplied by R squared. We can cancel here the R squared and we can cancel the R. You see here that we have KQ over R plus KQ over R. So it will be 3KQ over 2R. Okay? Minus KQ R squared over R cube. And this is our electric potential. We can go further with this equation to get V at the point D inside equal KQ over R over 2R factor of 3 minus R squared over R squared. That's all. We will put KQ over 2R in factor. Okay? Because here we have KQ over 2R and here KQ over okay, so it's not over 2R, so it's over R. 3 over 2. And we are done. Where is it? Yes. We are done. Okay, we forget here to put the 2 because it's squared. Yes. And we are done. Thank you so much. Let's move to another example. Okay, we are done with this example. Now we're going to move to the second part, electric potential due to charged conductor. Electric potential due to charged conductor. The electric field inside the conductor, as you know, is 0 because the charges are located or reside on the surface. The potential difference between any 2 points A and B inside the conductor is given by delta V, VB minus VA, equal minus the path integral from A to B of EDS, and it's 0. Why? Because what? Why it's 0? Because the electric field inside is 0. So we can say that any 2 points inside the conductor have the same electric potential. So the electric potential inside the conductor is the same. The results apply also between any 2 points A and B on the surface of the conductor. So the result also is valid for the surface. So what we can say that the surface of any conductor is what? Is equipotential surface. Why? Because our conductor is in electrostatic equilibrium, and we said that in electrostatic equilibrium the electric field inside is 0 and outside is perpendicular to the surface equal sigma over epsilon. Okay, good. Then what we can say, the electric potential inside the sphere is constant, as we said, and equal to that of the surface. So on the volume of the conductor, the electric potential is KQ over R. This is inside the volume, in the volume. Whatever it's on the surface or it's on the surface or inside. Okay, it's in the volume. The electric potential outside is given by KQ over R, small r, and small r is greater than the radius of this conductor. Okay, so we are done. Last example in this lecture, two spherical conductors of radii R1 and R2 are separated by a distance much larger than the radius of either sphere. The sphere are connected by a conductive wire. The charges on the sphere in equilibrium are Q1 and Q2 respectively. Find the ratio of the magnitude of the electric field at the surface of the charge. He's asking about the ratio of the electric field. We know that what do we know? The electric field produced by 1 is what? What is the electric field produced by the sphere 1? K Q1 over R1 squared. The electric field produced by 2 is K Q2 divided by R2 squared. He's asking about the ratio. That means we will divide. So it will be KQ, K, it will be cancelled. So we're going to get Q1 over Q2 multiplied by R2 squared divided by R1 squared. This is the ratio. But we want the ratio as a function of R only. R1, R2 only. Okay? We want the ratio E1 over E2 as a function of R1 and R2 only. So what we're going to do? So we have to express this Q1 and Q2. From where? From the electric potential. From the ratio of V, we can get V1 how much? Yes, V1 on the surface equal K Q1 over R1. And V2 how much? It's K Q2 over R2. What about the ratio? It will be, we will cancel this K, and we're going to get Q1 over Q2 multiplied by R2 over R1. However, what did we said about the electric potential when this on the surface of a conductor? These two spheres are connected by a conducting wire, so it will be the same. So we're going to get 1. So this ratio is equal 1. So we can say that Q1 over Q2 equal R1 over R2. Equation 2. And this is equation 1. We can write that equation 2 in equation 1. We get Q1 over Q2 is R1 over R2. Let's write E1 over E2 will be equal R1 over R2 multiplied by R2 squared over R1 squared. So what we're going to do, we cancel this R1 and we cancel the square, R2 and we cancel the square. So we're going to get E1 over E2 equal R2 over R1. That means E1 R1 equal E2 R2. And this is our relationship. Okay, we are done. So near the surface of the conductor, near the surface, what we want to do here, we want to write an equation of the relationship between sigma 1 and sigma 2, the charge, the surface charge density on the surface on the sphere 1 and the surface charge density of the surface of the sphere 2. Near the surface of the conductor, the electric field equals sigma over epsilon naught, sigma I. So that means if we have E1 R1, this equation, we have E1 R1 equal E2 R2 becomes sigma 1 over epsilon naught R1 equals sigma 2 over epsilon naught R2. Okay, so what we're going to do, we cancel this epsilon naught. That means we get sigma 1 R1 equal sigma 2 R2. Okay, very good. So if we want the ratio, sigma 1 over sigma 2 equal R2 over R1. But in our figure, you see that we have R1 is larger than R2. R1 is larger than R2. That means R2 over R1 will be smaller than 1. Yes or no? Yes, for sure. So this quantity is smaller than 1. So R2 over R1 is less than 1. That means sigma 1 over sigma 2 also less than 1. That means sigma 1 is less than sigma 2. And what we can conclude? If the radius of the sphere is smaller, the surface charge density is higher. And we can say that the surface density of charge sigma increases at a location of the conductor where the curvature radius decreases. If R2 is small, sigma 2 is higher. And we are done with this chapter. We take some examples. A solid spherical conductor is given at a net in a net non-zero charge. The electrostatic potential of the conductor is large at the center, large on the surface, large somewhere between the center and the surface, constant through the volume. Are we talking about conductor or insulator? In this example, we have a conductor. What we said for the conductor? In the conductor, where is it? In the conductor, the electric potential inside the sphere is constant and equal that at the surface. And we said it's around the volume, whatever on the surface and or inside. The electric potential in this case is KQ over R squared, over R. Okay, so it's constant through the volume equal KQ over the radius R. It's okay. This is the electric potential of a conductor inside the spherical. Good. Let's continue. We consider now two isolated spherical conductors, each having a net charge Q. The spheres have radii A and B, where B is larger than A. Which sphere has higher potential? Which sphere has higher potential? We know that V is equal KQ over R. If R is increasing, what's happened to the potential? Is decreasing. And we have B is larger than A. So that means VB is less than VA. Okay, because it's inversely proportional on the radius. Okay, so what we're gonna get? Which sphere has higher potential? Sphere A, of course, has higher potential because it has less radius. Last example, two conducting spheres are far apart. The smaller sphere carries a charge Q. Let's draw here. The sphere 1 has a charge Q. The larger sphere has a radius twice. This is, let's say, this is R. There is another sphere has a radius 2R. Okay, but it's neutral. Then, after the two spheres are connected by conducting wire, so we will draw the two spheres are connected with the wire. So what we're going to get in this case, the charge Q in this case will be distributed over the two spheres. Okay? Is it equally? Not equally, because we don't have the same the same volume. That means we don't have the same radius. The question, the charge on the smaller and the larger spheres are respectively q over 2, q over 2. No. Q over 3, 2q over 3, 2q over 3, and q over 3, 0 and q, this is no, because the charge will be distributed. 2q over and minus 2 minus q, this is no, because the charge is positive. So what we're going to do? How to demonstrate? So our answer is between these two. Is not equal, between B and C, for sure. Because it's not 0, because the charge will be distributed. It's not negative, because the charge is positive. It's not equal, because we don't have the same sphere. Okay, so what we're going to do? This charge Q, based on the conservation of charge, will be equal Q1 plus Q2. Okay? It will be distributed over these two charges. Very good. Without going through the calculation, we can estimate. We can estimate. Okay, let's continue. No problem. We can say that this capital Q is Q1 plus Q2. Good. And we have same V, because they are connected with a wire, conducting wire. So V1 equal V2. And V1 is what? Is K. Q1 over R1. And V2 is K. Q2 over R2. Good. And R2 is what? R2 is only 2R, because it has the twice the radius. Let's write this is R, and let's write this is 2R. And these two are equal. So we're going to cancel this K. Okay? Good or not good? Good. Then we will cancel also this R. So there is a relationship between Q1 and Q2. So we can write capital Q is Q1, and Q1 is Q2 over 2 plus Q2. So capital Q will be 3 over 2 Q2. The larger sphere has 3 over 2 of the charge. So that means the charge on the smaller sphere and the larger sphere are Q over 3 and yes, yes, good. That means Q2 equal 2 over 3 the initial charge. Very good. And we're going to get, this is for larger sphere. Very good. Okay. So if we want to calculate the charge on the smaller sphere, there is a relationship between the charge on the smaller sphere and the charge on the larger sphere. So it will be, so that means Q1 equal Q2. It's a 2 over 3 capital Q, and it's divided by 2, so it's 2. So we cancel this 2, 1 over 3. So Q1 is 1 over 2, 1 over 3 Q, and Q2 is 2 over 3 Q. Very good. We are done. Thank you so much, everyone, and see you in another lecture.